Hey everyone! In this next video and actually the future videos, it will be mainly for the H2 Math students, because for the A Math and H1 Math students, functions is basically a way for you to represent your equations, and that's pretty much it, alright? But for the H2 Math students, the fun starts now. And we begin with inverse functions, alright? So what are inverse functions? We are used to, or at least from the introductory video, we know that we can represent functions in another way, right? Let's say we have fx equals to x plus 3, simply making y equals to fx. So inverse function basically changes the whole thing. What do I mean? X was originally the input and y is the output. An inverse function reverses this, such that we now have x as the output and y is the input, where we have x equals to f inverse y. Now, a few things to take note here. Even though we have, it's kind of like raised to the power of minus 1, right? But generally, f inverse y is not 1 over fy, right? Or sometimes, as you'll see later on, f inverse x is not 1 over fx either, right? So do take note of this. It's not a raised to the power, but it's just a way to show that it's an inverse function. So this video is going to be split into 3 parts: solving inverse functions or finding them, proving inverse functions after learning what the conditions required for a function to have an inverse. Alright, so let's start with the simple one, finding an inverse function. So in this example, we have fx equals to x plus 3. Basically, let's say we want to find an inverse function for this fx equals to x plus 3. We simply start off with fx equals to x plus 3, and we let y equals to fx. Okay, now we have y equals to fx if and only if x is a inverse function of y. So the idea of finding inverse functions is basically letting x be the subject. Therefore, we have x equals to x minus 3, replacing f inverse y inside to give us f inverse y equals to y minus 3. Because we might want to actually plot this graph in the xy graph, and it's actually good practice to do so anyways, we want to change this to the original idea of x being the input and y being the output. Therefore, we'll replace y with x. This then leads us to f inverse x equals to x minus 3. Alright, and there we have it, the first example of our inverse function. Now, there's another example, that a technique that you guys will need to know. So let's say with fx equals to x squared plus 2x plus 3. Now, if you want to make x the subject, right? Now let's say we have y equals to x squared plus 2x plus 3. We just let y equals to fx, and therefore x equals to f inverse y. Now, if you notice, right, if you don't try the same method as before, you bring them plus 3 over to get you y minus 3 equals to x squared plus 2x. We then can't really make x the subject, right? Except that you can actually do something else, right? And this technique is very useful. It's called completing the square. Probably a very familiar technique. Why is completing the square a useful technique here? Because by completing the square, right, we're able to achieve the form of x minus h squared plus k. This then leads us to only one term having x, and that's about it. We can now make x as the subject, right? So from here, right, you can either bring 3 over and then complete the square. Otherwise, you can complete the square now. In this case, it's quite simple. We have x plus 1 squared plus 2. All right. We then have y minus 2 equals to x plus 1 squared. Now we take the square root of each side, but because it's a square, we then have x plus 1 equals to, very important, plus minus root y minus 2. Then we have x equals to minus 1 plus minus root y minus 2, leaving us with f inverse x equals to minus 1 plus minus x minus 2. Obviously, skipping some of the steps, such as letting it be f inverse y and then replacing y with x. Now here's the problem. There's plus minus inside the function, right? So how do you get rid of it? And the answer, right, is actually going to be the next part of the video. the conditions for an inverse function to exist. All right. So we had the graph fx equals to x squared plus 2x plus 3. Now the condition for an inverse function to exist is the idea of a one-to-one function. So there are two types of functions, one-to-one and many-to-one. The idea is that one-to-one function means we have a graph and there only exists one x value for one y value. All right, so every y value that you get, every output you get only has one corresponding x value. An example would be a linear graph. For a many-to-one function, there are multiple x values for one value. All right. Now take note, there's no such thing as a one-to-many function. There's no such thing as many-to-many function because they wouldn't be called functions anymore. All right. So multiple x values for one y value. An example would be a quadratic graph, right? If you notice at this particular y value, there are two possible x values. So for a function to exist, it must be a one-to-one function. All right, not anything else. Okay, so this is the condition for a f inverse to exist. That for f inverse to exist, fx must be a one-to-one. Fx must be one-to-one. All right. Now, if you look at the graph, right, of x squared plus 2x plus 3, it'll be this graph, correct? Where we have something like this graph, right? It's basically above the y-axis and is a many-to-one function. Therefore, for this graph to have an inverse, well, I can't really speak today, we must actually limit the graph, right? So let's say we either limit it from the to the left of the turning point, only to the right of the turning point, right? Because if you notice in this quadratic graph, right, it's basically over here, something around like this, where we have the turning point at let me work this out, a -1 and 2, I think, something like that, because we have x plus 1 square plus 2. Yes, so it's -1 and 2, -1, 2, right? So in order to limit the graph, right, we limit through the domain. But for it to be a one-to-one graph, it must be either on the green side here, because if you notice, if we only limit to over here, it's always a one-to-one graph. Alternatively, we'll do it from the right side of the minimum point, and you'll still be a one-to-one graph. But if you include the entire graph, or even let's say part of the left with the whole thing on the right, or whole thing on the left and part of the right, you get a many-to-one graph, which does not give an inverse function. So let's say for this example, we limit our domain to x less than -1. All right. Now, because x is less than -1, we know that it's a one-to-one function. Because of that, when we already worked out the inverse, right, to give us root plus minus root y minus 2 and -1 plus minus root y minus 2. Because x is now less than -1, this simply gives us -1 minus root x minus 2. Sorry, this should be x. Okay, so this is the whole condition for a inverse function to exist, and because this condition exists, you must take note of it, as this will then give us the proper way to find the inverse function, especially for a quadratic graph, right? Because it will help us eliminate the plus minus inside. All right. Now, to prove whether an inverse exists is the idea of the horizontal line test, right? If you notice in the many-to-one graph, I use a horizontal line. The idea is that for a function to be one-to-one, there's only one intersection point at every horizontal line drawing across it, right? If you notice, if I draw one horizontal line here, it's only one value. If I draw a horizontal line across, it will be only one intersection. However, if you notice for this case right here, if I draw a horizontal line, I might get two intersection points, right? So it's called the horizontal y equals to k line test, where one intersection point. Right, actually I should add only one intersection point at every k. Alright, or only one or zero actually. Yeah, only one or zero. Yeah, here we go. Okay, so this is the existence of an inverse function. Alright. Okay, so that's pretty much it for an inverse function. I will go through what happens, right, when basically the relationship between functions and their inverse in the next video. But for the meantime, this will be it. Alright, so there we have it, inverse functions.